My talk today is silicon photonics applications for 5G and data centers. I'd like to acknowledge my co-author and colleague, Dr. Dong Pan from Sifotonics Technologies. There is a high expectation for silicon photonics in our optical industry. From recent acquisition deals, for example, here you can see in recent years, there are actually many of these merger acquisitions of silicon photonics related companies. In particular, worth of noting is a $10 billion acquisition of Inphi by Marvell and Cisco acquisition of Acacia for $4.5 billion. From recent light counting forecast for silicon photonics based transceiver products, by 2026, the total sales can amount to $7.5 billion, and this is represented over 50% of all transceiver sales. Here I'd like to give a brief history of silicon photonics, get into the deployment for optical networking applications. For data center in particular, is the early silicon photonics based product rollout, represented by Luxtera and Molex combination, deploy the 40G PSM4 as a first generation silicon photonics for large scale volume deployment. Intel and Luxtera in the 100G era, they introduced the PSM4 and 100G CWDM4, and also get into volume production. In the 400G, 100G single lane, there's a Molex acquisition of Uplink recently, and this represents another new entrance for a data center high baud rate silicon photonics product rollouts. On the DCI front, Acacia deployed 100G coherent CFP in the 2013-2014 timeframe, and during 2016, there's a color Z, so-called color Z deployment based on silicon photonics by Inphi. And recently, Acacia introduced 400G ZR and ZR Plus in variety of form factors around 2019. At Sifotonics, we are approaching silicon photonics deployment in a different direction. In the early 2011, 2012, we actually rolled out the 10G germanium silicon PD, APD, primarily for telecom applications. Subsequently, we introduced 25 gigabaud germanium silicon PD and an APD targeted for 5G applications. And by 2017, 2018 timeframe, we introduced 53 gigabaud germanium silicon PD and APD. This can further support higher baud rate, such as 100G per lane new optics. And we also introduced 4x100G germanium silicon PD for 400G applications, as well as 100G, 400G coherent PICs. And just last few months, we introduced a new class of silicon photonics germanium silicon APD-based product, so-called 8x100G ER1 NWDM product solutions for 5G front haul deployment. For 5G and data center optical solution sets, in particular, 5G front haul requires low latency, high bandwidth. And in many cases, fiber availability utilization is an important consideration. And this really drives WDM optics deployments. And throughout the 5G front haul, mid haul, back haul, there's range of technologies need to be deployed. From data rate point of view, anywhere from 25G to 400G, and then from the reach point of view, front haul in particular require low latency, so 10 to 20 kilometer is the maximum distance requirement. From the mid haul to back haul, there's a wider range of 10 kilometer, 40 kilometer to 80 kilometer plus type of deployment. Then you look at the WDM mix, you actually start to see, so there are a variety of WDM types deployed in these optical networking applications. If you look at the metro DC, there's a transition from 100G DWDM to 400G DWDM. And inside the data center, there's also an upgrade cycle just happening now from 100G to 200G and 400G. In particular, take an example of 5G front haul solution. For Chinese service providers, 25G MWDM promoted by China Mobile and LWDM promoted by China Telecom. They pick different wavelength sets within the O-band spectrum. 10 kilometer is typically require a minimum reach. Germanium silicon PD and APD are deployed for these type of applications. And in particular, germanium silicon APD require for extra link budget. There are a few scenarios why this extra link budget is required, even though this is 10 kilometer reach. In some cases, protection switching is required, that adding the additional insertion loss to the data link. And then for MWDM, if you're looking at a high wavelengths, 1351, 1371 nanometer, for example, there are extra link budget required for dispersion penalty allocations. If you look at the silicon photonics based 25 gigabit germanium silicon APD, I like to highlight the advantage here. First of all, germanium silicon APD, to use germanium as an absorber, which is a very wide optical spectrum range from 800 nanometer to 1550. So it's a very versatile absorber material for detector. On the other hand, silicon as an avalanche material, it actually has a superior gain and noise performance. And then combined with a standard CMOS epi process, that drives a good economics with high volume applications. And one of the critical factors for germanium silicon APD is high epi quality is very important for low defect rates and low dark current. And we have demonstrated very high performance of industrial temperature in high volume production environment. In the upper right corner, we are showing a 25 gigabit per second germanium silicon APD over temperature range from -40 to 85. And they produce a very good sensitivity performance numbers to meet the 5G front haul type of applications. And to date, we have deployed the germanium silicon APDs in very large numbers. And here we are showing cumulative device hours in the last 2 years, achieving over 10 billion device hours cumulative deployment with excellent, very low feed rates. Here is another new example of 5G front haul solutions. We recently introduced a 8x100G ER1-NWDM. This is actually enabled by a 50 gigabaud germanium silicon APD to support 8 channels of 100G going single wavelengths and extended distance with WDM capabilities. In this case, wavelengths from 1295 to 1311 nanometer with 8 wavelengths, 400 gigahertz channel spacing at near zero dispersion window. So we can support up to 20 kilometer transmission with minimum penalty and with allocation of WDM mux, DMux, and airdrop loss already included in the link budget. And this enables a very low latency WDM for 100G. In this example, you can actually use these wavelengths as a 4x100G upstream and 4x100G downstream to enable a bidirectional single fiber transmission. And you can enjoy pay-as-you-grow economics for the end users. And here is a 53 gigabyte APD we'll be presenting at OFC 2021 in a well-packaged 53 gigabaud germanium silicon avalanche photodiode ROSA. So this is basically now from device level to a fully packaged components which can goes into the module product solutions. And we compare 50 gigabaud NRZ, which can achieve high sensitivity down to minus 23 dBm at 1E minus 3. And at 50 gigabaud PAM4, we can actually achieve minus 16 dBm at BER of 2E minus 4. And switch gear to 5G mid-haul and backhaul solutions with germanium silicon APD. Here, traditionally, going over long distance, extended distance, people use 4x25G germanium silicon APD in the form of 100G ER4 Lite or 100G CWDM4-40. So these are 30 to 40 kilometer 100G transceivers, however, using 4 channels of transmitter and receiver. And new type of single lane 100G extended reach is now released by 100G Lambda MSA as a release spec, enable industry now to deploy 30, 40 kilometer with single channel 100G PAM4. And this is also enabling a smaller form factor such as SFP56DD, which can support very high density switch routers. In the right-hand side, we are showing a receiver BER versus input power in OMA. And you can compare it to 100G ER1-30 and 100G-40 spec, and over temperature of 0 to 70 degrees C. So this is test results on a actual built transceivers. And we'd like to discuss also silicon photonics MZM supporting the extended reach 100G. Here we are showing advantage of silicon photonics MZ modulator versus a typical 3.5 base EML. The Mach-Zehnder modulator based on silicon photonics can provide consistent low chirp property with improved dispersion tolerance. And it does not require thermoelectric cooling to produce good extinction ratio performance. And here we are showing two samples against the minimum and maximum dispersion tolerance range, typically supported by the commercial available DSP. So you can see less than 1 dB of dispersion penalty can be achieved consistently. In this chart, we are showing 100G Lambda MSA supporting 100G ER1 and 400 ER4. This is a new type of new generation of product really fill a gap in terms of a new type of optics supporting 100G and 400G for extended reach. With 30 kilometers actually allow a wider wavelength range because of relaxed dispersion requirement, and it can support up to 15 dB link loss budget. For 40 kilometer, it requires more precise wavelengths of 1309 plus minus 1 nanometer, and it can support 18 dB of link loss budget. MSA release 1.0 already released, with revision 1.1 is up and coming. For 400G ER4, utilizing the same foundational technology of 100G extended reach combined with the NWDM 400 GHz channel spacing, the spec can meet 30 kilometer reach with very minimum dispersion penalty, and this revision 0.2 about to be released currently is still in MSA members review process. Let's shift here to the telco core and metro and DCI solution space. In this case, there are two solutions can be applied to the metro high bandwidth requirements. For the gray optics, so to speak, this new 400G ER4 solution can support QSFP-DD or OSFP. In addition, this can also support 4x100G ER1 NWDM interoperability, so a breakout scenario can also be used. And this is enabled by 53 gigabaud germanium silicon APD. And the wavelength range, as we indicated in the upper right corner, it ranges from 1306 to 1311 with 400 gigahertz channel spacing. And the dispersion range, the worst case dispersion range can be managed to from minus 56 picosecond per nanometer up to about 37 picosecond per nanometer in the positive maximum side. For DWDM type of applications, silicon photonics, ICTR, and IC TROSA can be the building block to support 400G ZR or 400G ZR plus QSFP-DD or OSFP. And there's a recent demonstration by Arista using such OSFP devices for the DCI solution set. Inside the hybrid data center, current generation deployed in volume is 100G module we discussed earlier. It's based on 100G PSM4 and 100G CWDM4. These are based on 4x125G optics, and 4x25G germanium silicon PD array already being deployed in this type of modules in high volume. And there's a transition over to 200G in some of the data center applications. These 4x25G germanium silicon PD array can also be leveraged for these applications. And then for 400G DR4, we are starting to see volume deployment starting last year, and will start to ramp up this year. You will start to see two silicon photonic based technology supporting this field. For 3.5 EML based constructions, 4x50G GBOT germanium silicon PD array can be used on the receiver side. Then for a full silicon photonics build, we can provide a 4x100G silicon photonics with Maxano modulators and germanium silicon PD array all integrated in one chip. And going forward, we already start to see 800G modules start to be built and to be demonstrated. And this is probably going to be in the form of 2x400G DR4. And in our industry, we also start to discuss so-called co-package optics. There's OIF project already started with this officially. So there will be a MSA supporting this co-package optics. In Gen 1 deployment is most likely going to be a 3.2 terabit per second with 32 by 100G optics. This is also supported by the OIF project. And most likely scenario for deployment is for 51 terabit per second or 102 terabit per second switch generations. From estimated time frame for such deployment, I think in general, we are talking about still 2 years away, maybe 2023. Here we are showing a novel CPO solution proposal with germanium silicon APD. A 3.2 terabit per second CPO in general may require up to 16 external lasers to power 32 modulators, even with 1-to-2 split on silicon photonics chip. Here we propose to shift the link budget burden from TX power to RX sensitivity with germanium silicon APD type of high sensitivity receivers. We have demonstrated 53 gigabaud germanium silicon APD can meet minus 14 dBm OMA type of sensitivity. This is actually 10 dB better compared to current IEEE 100G DR or 400G DR4 type of spec. With 9 dB shift, we can reduce laser count by 88%. In terms of a 32 by 100G, is possible use 2 lasers to power the whole 3.2 terabit per second. And this came with a great advantage of reduction of power, cost, complexity of laser coupling, and also with much improved yield and reliability. And here we are showing a optical networking technology roadmap summary. In the horizontal axis, we are showing the data rate increase from 25G, 100G, to 400G, 800G, and 3.2T. On the vertical axis, we are showing the distance spanning from 500 meters to 80 kilometers. At low speed, like 25G, NRZ modulation is exclusively deployed. In the 100G generation, there is a mix and transition from 4x25G NRZ to PAM4. And for the longer reach, such as 80 kilometers, a coherent technology is already utilized. And the latest introduction of 100G R1 is extending the PAM4 modulation to cover up to 40 kilometers. And going to higher data rates, we can see in the 400G generation, we are also adding a PAM4 generational optic to support 400G 30, 40 kilometers. However, the coherent technology is increasingly taking a bigger share and coverage of the distance supported by higher data rates. At 800 gigabit per second, there's already discussion if the 10 kilometer can be supported by direct detect PAM4 or coherent technologies. So we can see in this chart, if you moving forward, the exclusive domains of complex modulation, either by PAM4 or coherent, is going to be the technology of choice and baseline for silicon photonics solutions. Here we are showing a complete mapping of silicon photonic technologies, covers all the different applications. You can see the germanium silicon PD and APD primarily cover the direct detect, both for lower data rate up to 400 gig, 800 gig, from short reach to extended reach applications. And silicon photonic integrated magnetic modulator and PDs already are deployed in high volume for 100G and transition to 400G, and will continue to support majority of the shorter reach applications all the way up to 1.6T or 3.2T. Again, increasingly, the silicon photonic coherent integrated circuits and PICs will cover extended reach, beyond extended reach to 80 kilometers or more at 400G and below, but increasingly going beyond 400G, silicon photonic coherent PIC will cover as far as 10 kilometers or even lower. There's already also discussion at 3.2T, there may be opportunity for coherent to go inside data centers. In summary, we'd like to discuss what is ahead for silicon photonics in the next 10 years. In data center, we anticipate to see so-called opto switch may become the mainstream, which require the CPO or silicon photonic chiplet to be very closely integrated with switch IC or router ICs. And then there are a particular area of AI and machine learning. There may even be photonic computing core also start penetrating the data center AI and machine learning computing platforms. And if you're looking at the left side, there will be a plethora of applications driven by high volume silicon photonic deployment from baseline of communications into the sensor area, such as LiDAR, 3D cameras, and medical personal health applications. And if you're looking at the middle, that's where the connection between the end application to data centers, coherent detection will extend further to the edges, starting from today's DCI and Metro. Increasingly, they will cover much wider range of applications to the edge networks. And there's also interesting deployment now in the communication satellites, such as Starlink. And there are high anticipation that coherent intersat free space communication also may start to deploy silicon photonics based technologies. And then if you're looking at the first 10 kilometer or first few miles of directly to the end user home or mobile applications. Here, we anticipating the germanium APD high sensitivity direct detection will start to dominate. In summary, silicon photonics now finds very wide range of applications in 5G data centers. Germanium silicon APD is becoming an important part of the optical networking toolkit, increasing link budget for 25G front haul, for example, and extending transmission distance at high baud rate for 100G and 400G. And in addition, we're also showing this new category of capability also enable a 100G O-band WDM for front haul. And we also propose a new concept to reduce laser counts for highly integrated high channel count CPOs. Silicon photonics supports 100G PAM4 direct detect and coherent detection applications, and is becoming foundational networking technologies with increasing speed per lane and lane counts by the wide range of data center applications going forward. We anticipate silicon photonics becoming mainstream for optical networking and also start to contribute to many new emerging applications such as LiDAR, 3D sensors, computing, and biomedical applications. Thank you for your attention.